So I will present IRT Jules Verne shortly. I will present two applications that we have done with ROS and Motoman robots. I will speak a little bit about the driver aspects and the next steps that we have. So IRT Jules Verne is a research center located in the other side of France, in the west. It was created in 2012. We have like 150 people working on it and some patents. And we mainly work for the industrial ecosystem in manufacturing. And one particularity is that we have industries around us that work with very large parts, like Airbus or Naval. So they build boats, big planes. And it means they build only a few per day or per month or per year sometimes. So it's very difficult to put robots in this situation. Most of the work still remain manual, but we are pushing for that. So this is where we are. So what I just said, the other side of France. We organized the ROSCon last year, so we are very happy to come back. And our missions are to boost the competitiveness of the factories, to accelerate transfer, and to support manufacturing activities. And we have 5 teams. One team is dedicated to metallic applications, metallic processes. One team is dedicated to composite processes. One team is dedicated to simulation. One works on monitoring. And then there is my team in robotics. And what is very particular at IRT Jules Verne is that we are not the best in robotics or the best in monitoring, but we work together. So we develop applications that make use of combined skills. So you will not find a team of 50 or 100 roboticists. We're only 20. But we combine with 20 others that are good in composites or 20 others that are good in control. These are some of the robots that we have built or partially integrated ourselves. Large positioners for assembly of planes, mobile manipulator for inspection of large parts, and cable-driven parallel robots for large volumes. The two applications I wanted to speak about, the first one is part of an European project called Cogniman. It's about medical part finishing. So the implants that you have in your knee or somewhere else, mostly done in metal, in titanium. And some of them are 3D printed because every person is different. So you want a shape which is different per person. And you want to do it fast because people are waiting. So this requires some complex tasks. First, when the part is printed, you have to remove it from the support, remove the support that comes with the 3D printing process. And then you have to polish the part, but not everywhere. You want to polish the parts where they are in contact with soft materials, but in the places where they are in contact with bonds, sometimes it's better to leave them rough because that improves the gluing with the bones. And then there are these medical quality requirements, and the fact that you work with these 3D printed parts is unhealthy for workers because the titanium powder or the aluminum powder is not so good to breathe. So by introducing robots, we can improve not only the business case, but also health. What we needed was to polish the part selectively. So we wanted to use ROS control. We wanted to use the force aspect of the ROS control. As you see in the right, we are polishing or finishing the part using the Motoman robot. So this is the first application that we worked on with this robot. The second application is about welding, large offshore structures. So these are floaters. They weigh like 85 tons each of the 3 branches. So at the end is 150 or 200 tons. And as you can see, what we have to weld is 9 meters by 9 meters by, it's a square of 9 meters. So which adds up to 40 meters, but then you have to go more than 10 times on these 40 meters. So at the end, you have more, it's actually like 20. So it's like welding 1,000 meters. What we want to do is to reduce the amount of people that need to monitor the application. Because today, when you are welding, there is one guy behind the welding device that is correcting the position all the time, or the parameters. So we wanted to automate this. We did the first steps in a Motoman robot. It's not the one that will be used in the offshore, but it's the one that prepares the application. And people that work with the Motoman robots are used to do the program themselves. So they take the teach, they put the start point, end point, and they connect them with the moving line. Then they add the arc on, arc off structures, and they're finished to do the job. So we didn't want to have them use ROS as a whole. So we want them to keep their know-how on the way they work. So we just add something that says start the correction, stop the correction, and the rest, for us, is like not visible. Sorry. So here you can see the sim tracking working. So the robot is starting to move, and as you can see, at a given point, it reaches the part, and it starts correcting and following the sim. It's not a straight sim, so it has to compensate continuously. Normally, the sims are straight, but we wanted to test our driver and our solution. Another difficulty is that when you are welding, your torch is not, sorry, this is the same, right? Okay, when you are welding, the torch is not just moving in a straight line. You have an oscillation. So we want to compensate the sim tracking while the robot is oscillating. So we need to know very well how this oscillation is working. So we needed to introduce in the driver the fact that it can measure the robot position quite accurately to compensate for this oscillation. So as you see here at the end, the first part is okay. When we start oscillating, we get a different image from our profilometer. So we needed to calibrate the profilometer on the robot position, on the hand. So we did that using a sphere. And then we needed to compensate as well as possible, as much as possible, for these oscillations. As you can see, it's not quite visible, but the line, I don't know if I have a light here. So the lines are quite straight if you look at the upper lines, and the fact that it moves outside is just because the laser profilometer moved. But actually, the straight lines remain straight. So we are actually compensating for this oscillation quite well. So how we did that? Actually, Motoman has already a driver, which is Moto ROS, which is already in ROS2. The current solution of the driver uses micro ROS, which was developed in an European project. So you install micro ROS inside the robot with a USB key. And then you have a micro ROS on your PC. These two guys speak with each other, and then you put whatever you want to do in ROS. What we did was very similar, so we compile a module using Moto Plus inside of the robot. So this is the module that will communicate with the ROS driver. And then we have two choices, either a hardware interface for ROS control or a direct Cartesian driver for ROS applications without ROS control. Actually, I put this diagonal line on the second one because we are pushing for having just one solution, the ROS control solution. So we hope to have just one of them doing both applications. What is interesting in Motoman is that you can compile inside C code directly inside of the robot. The big challenge that was solved by Motor ROS was to put ROS inside of a robot where the resources are very, very limited. So this is why micro ROS was chosen. So the whole ROS stack is inside of the robot. We didn't do that. We have only a small communication to the robot. In terms of performance, Motor ROS allows to program trajectories, full trajectories up to 200 points, even more if you have single robots, but that's a limit. So you cannot do more than that. You're limited to fast DDS. eProxima is because of the micro ROS in the system, and it works at 1 hertz. What we did is that we correct the Cartesian trajectory, which was programmed by the welder in GBI, which is the Motoman format. We can see the absolute joint, we can correct absolute joint motions for the force controller, and we tested with the ROS control admittance controller. The communication is just UDP, so this part remains dedicated to the communication with the robot, but after that you put any ROS communication. So you're not limited to fast DDS, and we managed to push up to 250 hertz. As I said, for the welding application, it was very important to respect the way welders work. And for the medical application, we wanted to take advantage of ROS control. So what's next is pretty much what we have seen from Felix and, sorry, I forgot, from FZI, Robert. So we want to put this open source this work. But before we do that, we have to check that we have a good maturity. We have similar problems to Felix described for your robots. There are many Motoman robots and controllers. So we want to check that it does not only work with the ones that we have tested, but with others. We want to discuss with Guys van der Haan, the developer of Motor ROS, to try to, we don't want to be in concurrence, we want to work together with them. We want to discuss with Yaskawa so we can get some support of them from their side. It's not imposing something, ROS, that they can check that it's sure it corresponds to their expectations. We have to make the documentation. As described by, I forgot again, by FZI, something we did also is that the force sensors the force sensor information is going through the robot. So we can avoid a force sensor interface in ROS or use it. If you want to use it, you're in the ROS world. But if not, you can take advantage of the robot doing this interface, which is already there provided by Yaskawa. We have already a GitHub place, but the driver is not yet there. It will be there. And for technical information, you can speak with Ludovic Delval, which is not here. He's preparing a workshop right now at the ROSCON. But he will be the guy that will open source and deploy this. Thank you.